Hello everyone. This is a short screencast in which I'm going to describe how we create a motional EMF. That's not emotional. That's an EMF that would be crying a lot. This is motional, which means we use motion and a magnet to create what is totally equivalent to any other EMF, which is short for electromotive force. The most familiar example for most people is a battery. So you might say, as I did here, how to make a magnet act like a battery. The best place to start to understand motional EMFs is by using the Hall effect, something you learn in your first study of magnetism. The Hall effect describes how we can separate positive and negative charges on a piece of metal that is moving through a magnetic field. So here we've got this rightward moving piece of metal, and of course the electrons inside of it are moving rightward also, and therefore they will experience what's known as the Lorentz force. That's the force of magnetism on any moving charged particle equal to the size of the charge times the velocity times the size of the field that it is moving through. And in this case it's perpendicular to the motion, and so we don't need any kind of cross product involved. So because of that, and it's shown here, the magnetic force on this negative charge, drawn in blue here, is downward, and so we'll get this collection of negative charges at the bottom, leaving behind, of course, positive charges up here at the top. So you might think, well, we're just going to keep accumulating a bunch of charges, but as we build up the separation of charges, then we have an electric field, and it's kind of hard to see this. They've got it drawn here with a red vector, but it's being overlapped by a couple other vectors. But that downward arrow there shows the electric field that eventually prevents other charges from moving. So when will we strike a balance? Well, we'll strike a balance as soon as the electric field balances the magnetic field. And on every charge, we have an electric force equal to QE, and the magnetic force QVB. And when those two forces are balancing each other, then we have created a potential difference across that piece of metal. And that's the biggest potential difference we'll ever get. So let's write an expression for this potential difference. First thing I'm going to do is cancel out these Q's. It shows us that the charges don't matter here. And then I want to remind you of an important relationship between electric field and potential difference. And that relationship is that the electric field describes the potential difference across some separation. In this case, it's the separation L. That's the distance between where we've collected positive charges and negative charges. And what we have on the other side is VB. So as long as we keep moving this piece of metal rightward through that field, we will establish a potential difference, delta V, equal to V times B times L. Now I want to caution you here that we have a capital V, delta V, used for potential difference, and a small case v used for the velocity of the piece of metal. And those are easily confused when you write them by hand. So there's an example of building up a potential difference, what we call the Hall potential, across a piece of metal. So now let's compare that with what happens if we take the same piece of metal and we arrange it like this. Now we've got a couple of metal rails, those are shown in the orange, and we've got a wire with a little resistor connecting it, but otherwise everything is exactly the same. And you might think this looks totally different, but the truth is we still have a potential difference built up across that piece of metal that's moving rightward. But the difference now is those charges don't have to accumulate anywhere. That potential difference will actually be pushing charges or current around this loop. So we can see here drawn in blue shows the direction that positive charges would move if, of course, they were able to move. And if I fill in the other remaining lines here, these blue arrows represent the current traveling around that little square branch. Of course, that square, or what looks like a square now, isn't going to look very square later as that bar continues to move rightward. But as long as we continue to move the bar, we will generate that current. And when we generate current, we call that an EMF. It's measured in volts, just like the potential difference. And so all I'm going to do here is continue on with what I had before, but I'm going to change symbols. Instead of delta V, I'm going to call this now the EMF. That's kind of the script looking E, but the quantity is still calculated the same way. So it's due to the motion of the bar itself. Somebody's got to be pulling on it in order for this to happen. And then the field, and then the length of the bar, which is also shown here on the figure. That's just sometimes called the width, but it's important that that be the dimension of the bar perpendicular to which way it's moving. And so that EMF is what's driving the current around this particular circuit. So if we draw a little circuit diagram, it actually looks very familiar. This is just a resistor with current going through it, and that current is being generated by an EMF. What's different here is instead of like a 9-volt battery or something, we have a motional EMF. Just a little space here to write how big that EMF is, and it's equal to the quantity of V times B times L. So if I need more EMF, I can just speed up my velocity, or I can turn up my magnetic field, or of course I could totally build the whole thing differently and maybe make a longer bar. But that gives me the ability to create any kind of EMF that I want. Now, this is the starting point for understanding electromagnetic induction, is motional EMFs. The next step is to show that it is totally equivalent to what is referred to as Faraday's law. So, in another segment, I'm going to show this exact same derivation starting from a totally different point, but we will end up with the exact same EMF. So that'll do it for now. Hope that was a good start.